to speak mainly about the halting problem, and I'm going to unveil the paradox of assuming that everything can be computable. As from when we are at a young age, we just think that anything can be done with a computer. The only thing I thought was not barely reasonable to uncomputable was in cryptography when people used to say that the time taken to decrypt something will be in the order of million years. That's the only thought of something I had as uncomputable. But saying that something is actually uncomputable with even if you had infinite time is a pretty bold claim, and we are going to do that today. So there are three main problems with logic at the start of the 20th century. So logicians were after they found many contradictions like Russell's paradox and also they wanted to formalize the whole base of mathematics. So they started with the ZFC axiom, and so they had a few questions about the ZFC axiom system and about just axiom systems in general. That if you have a finite set of axioms, are the following claims true? So the first claim that was is the axiom system complete? That is every theorem can be proved true or false? That is a very useful thing to know, so that at least we know that everything can be proved at least. The second thing is it consistent? So how are you sure that your axioms don't creep and give it a contradiction? And if it gives a contradiction, we know that we have to say that the axioms are not consistent and we have to come up with a new set of axioms again.
And the final one was decidability. So decidability is going to be the main topic of what I'm going to talk today. And it asks the question, is there a procedure or an algorithm which decides if an input belongs to a set or not? Like how I'm going to ask, is 2 belonging to the set of even numbers? So the first two problems out of the three problems was given by Godel. So Kurt Godel proved that in a consistent formal system of arithmetic, there will be statements about natural numbers that are true but cannot be proven at all. So the first statement was proven false. He also proved that a formal system cannot prove that it's free of contradictions. It might be free of contradictions, it might be consistent, but he proved that a formal system itself cannot prove anything about itself. So it can't prove that it is consistent. So it doesn't mean that the system is inconsistent, but it cannot prove that it's consistent there. So now we got to know that mathematics is incomplete and it cannot prove its inconsistency. So now we were left to the only hope that maybe we can decide it was decidable, and maybe we can, as Deepak sir told, we can make a computer which can decide everything for us. But no, Turing showed that mathematics is not even decidable. So we want to construct a problem which is not decidable first of all. So first, before constructing a problem which is decidable, we want to dig deep into the relation between computable and decidable, because they are pretty similar terms but different in their own aspects. So a function is said to be computable if it can be computed or solved by an algorithm. That's almost like a self-referential definition. But decidability is more to decision problems. So if you have to decide if something belongs to a set or not. So it's you have two options. It either belongs to a set or it doesn't belong to a set. So if you can decide if it belongs to a particular set, so all decidable problems, they're obviously computable because you're able to decide it. That means you can obviously solve it using an algorithm or just using pure knowledge. So any non-computable problem which has only two options, like 1 or 0 or yes or no, is non-decidable because they come in the domain of decision problems, but they can't be computed. So now Turing tried to show a non-computable problem with two choices, namely the halting problem. So before we talk about the halting problem, we need to first define computability, because the definition of computability I have given here is just like if it can be computed by an algorithm. That's a very vague definition and self-referential. You are computable if you are computed. That's a very vague definition at that time. So Turing tried to strengthen the definition of computability. So first of all, Turing made a Turing machine, which is a theoretical model of computation. So he assumed the Turing machine consists of a long tape, which each have divided into a lot of cells. So it's like maybe a large memory portion in your computer, and you are dividing into a lot of bits. So like each bit can store a symbol. In computers is 1 and 0, but in a Turing machine, you can store any symbol which is possible in his language. So then the machine has a head which can move left or right along the tape so that it can move to other cells, and it can read the cell what is on, and it can write something on that. It also has a control unit which determines its behavior based on the current state and symbol being read. So like the control unit is something like the CPU of a computer. Depending on what we give it, something like a symbol being read is our input, and the current state is like what the CPU is currently is like. Maybe the CPU is in a state of maybe it has to run a program, so it's in that state. So now depending on that state and symbol being read, it follows a specific instruction so that it gives a proper output. So this machine operates using a particular set of rules or instructions. And we need to note that the rules and instructions here are finite. And the number of states which the head of the Turing machine can be is also finite. We don't want it to be infinite because that can easily cause it to be an infinite loop, and we don't want that. Like here we see that it reads the symbol 1, and initially it's in the blue state. So using this information, it's in a blue state, and it read the symbol 1, it's going to decide what to do. So it's going to decide what is going to be its next state, maybe like the yellow state. And it's going to decide if it has to move left or right, depending on its instruction set. And it's going to decide if it's going to change that 1 to a 0 or just going to keep it as a 1. Pretty simple, right? So this was one theory of computation made by Turing. So now let's look about one more theory of computation made by Alonzo Church. So he made a theory of computation called as Lambda Calculus, which is one more way of studying computation and saying what is computable. So like it's a mathematical framework of expressing and manipulating functions using a small set of rules and symbols. So it has a small set of rules and some symbols where you can manipulate using the rules. And with that, you might get after completing the rules, you might reach a place where it halt, or it might go on forever in a loop, like coming back to the same expression as it was in the initial expression. And after doing some operations, you come back to the initial one and goes for an infinite loop. Or it might just halt after like reaching a specific state. Interestingly, this was published before Turing published his work on Turing computers. But and because this was published before Turing had to rush his publication on the Turing computer. And just before he published this on the Turing computer, he provided a proof that anything computed by Lambda Calculus could also be computed by a Turing machine. So basically, he gave a proof that Turing machine is at least as strong as Lambda Calculus. That is a good thing to say, because right now we don't know if Turing machine computes everything or not. So at least he's saying that it's at least as strong as Lambda Calculus is something like it's at least better than that. So why is the Turing machine more popular than Lambda Calculus? Although Lambda Calculus was published before Turing computers, Turing computers are way more simpler and it's more easier to understand than the complicated language of Lambda Calculus. Turing machines make it more easy to visualize and try to like make a program out of it. And Turing machines have also been implemented in many computers, as Deepak sir has told. So like it has, as more computers have used it, there's more knowledge about it rather than Lambda Calculus. So it's more practical for executing computations as well. And one more thing is like Turing machines have proven to be equivalent in power. After that, Turing proved that it's stronger than Lambda Calculus. Then like other people have proved it that even Lambda Calculus is as strong as Turing. So they are equivalent in power. So you can use any one of those. It shouldn't make a difference. So first we are going to talk about deterministic Turing machines. So deterministic Turing machines are very similar to the deterministic algorithms or the normal algorithms we learn. So like a deterministic Turing machine is a type of Turing machine which operates according to like fixed set of rules. So like if we have a specific state, like the last time we had seen that was a blue state and it read a symbol 1. So this type of Turing machine will always perform the same action. If it gets the same symbol blue state and the symbol 1 3 times, it will do the same action for 3 times. That is, there exists a function which reads the input state and what it reads. And it like outputs the output state and what to write, and if it's going to move left or right. So like this is very useful for us because if this is the case, that means we can easily like know what is it going to do next. As if we can easily know what is going to do next, at least it'd be easier for us to fact check the program if it's correct or not. And even the rules will probably be not so complicated. There's the next set of Turing machines which are non-deterministic. These are similar to the randomized algorithms we learned in class. So a non-deterministic Turing machine operates a non-deterministic rule. So sometimes like unlike a deterministic Turing machine, a non-deterministic Turing machine has multiple possible moves at each step, leading to a lot of different possible cases which we have to consider. It's like a randomized algorithm where you'd like try to flip a coin sometimes, and if it comes heads, you go in one direction. If it comes tails, you go in one direction. But finally, the output given by a non-deterministic Turing machine and the deterministic Turing machine should be same for the same operation, or else there wouldn't be a point of using this. And we try to show that both are of the same power. There's not going to be a concrete proof, but rather an overview of how it is going to be. So it has been shown that anything which can be computed by a non-deterministic Turing machine can also be computed by a deterministic Turing machine. This is because like whenever you do a coin flip and you try to go for 2-3 ways in a non-deterministic Turing machine, in a deterministic Turing machine, you can try to go in all paths separately and choose the path which works. So like given more time, deterministic Turing machine can try to mimic the non-deterministic Turing machine by trying all the possibilities. So given more time, it should be able to do as much as the non-deterministic Turing machine. So they both are the same power. So as we don't mind about the time right now, because we want to show that something is not computable given infinite time. So we are going to talk about deterministic Turing machines from now. Now we go to one more type of Turing machine, which are known as the multi-tape Turing machines. Similar to the single tape Turing machines, which had one tape and one cell. Like the single type Turing machines have one tape and each has a lot of cells. So multi-tape Turing machine has more than one tape, and each tape has a different head, which can do its operations independently or coordinated with each other. So like these tapes are parallel independent tracks, which each of the head will read a symbol from its own tape and do the instructions given to it for that thing read. The interesting thing is that these tape heads can even be coordinated and synchronized. This means that like maybe if you have two tapes and when you have two tapes and two heads, maybe you want to do something when both the tapes read a one only, not like they're independent, but only if both the tapes do a one, you want to do some action. That is possible with this. But with single tape Turing machines, it's a bit harder to try to do that. Like try to like coordinate two actions will be more difficult to do. It's not impossible, but it's still harder and it takes more time to do that. So we want to show that the multi-tape Turing machine is same as a single tape. So we are going to like say that it's going, you can just like concatenate the tapes. Like you have two tapes and each of the tape has a finite set of instructions because you can't expect a computer to like do infinite set of instructions. So as it has a finite set of instructions, you can concatenate the two tapes. And then first you need to do instruction of the first tape, then do an instruction of the second tape. So when you do these both, you decide based on the outputs of both of this by remembering the what the first thing was done, which can be done, like it's just an assignment operation. So remembering the thing what the first one does and seeing the output of second one, do a particular operation for both of them. And then again go back to the first one, do the next operation for second one, and keep on alternating like this. So when you keep on alternating like this, it is similar to as you're doing a multi-tape computation. The only thing is going to take up more tape space here because like you need to give indicators that when the second tape starts or where are you in the second tape when you're doing something in the first tape. You need to give an indicator to the head that I stopped here at the second tape. So from the next time I'm going to start from here. So maybe it's like in computer when you need to say that right now I'm doing this process, but in this process I've been stuck here. So when I'm going to the other process, I need to start from this particular checkpoint or something. So you need to keep some symbol for a checkpoint there. So now because like it would take more memory, but nonetheless with given more time, you can do the same computation. They have the same computational power. So we want to only talk about single tape deterministic Turing machines. Next, we come to the very profound idea of computer science, where we say that code is data, data is code. So this means that because there are like different Turing machines which do different things, like there's a different Turing machine for adding something, maybe for subtracting two numbers, maybe for multiplying two numbers, there's a different Turing machine. So they have different instructions on the particular state and the symbol they read. Now these instructions, they're also part of a binary code. If the initial instruction set is given in a binary code, even the head instructions is a binary code. And you can even give the head instructions to the Turing machine. The output of the Turing machine uh, might be garbage. Like if you want to say add two numbers and you give the two numbers as the code for subtracting two numbers, that code has one input, and the code for multiplying two numbers as an input. And if it adds those both, the output makes no sense because they are not numbers. But nonetheless, you can do it. It's possible. So this leads to, as Deepak sir told, the self-referential part of computer science. And as we know that the self-referential characteristic of first order arithmetic leads to a lot of paradoxes. So we're going to show that this is going to lead to a paradox again. So this idea that data is also code has a profound impact in computer science and programming languages. So now we are going to make a universal Turing machine. This Turing machine is like a all-purpose Turing machine, like our computers, which we can do to do anything. It's not a specific purpose. This Turing machine should be able to do everything what it wants to do. So a universal Turing machine is like a theoretical Turing machine, which can simulate any other Turing machine. So for this, you're going to give the instruction set of the original Turing machine. So the instruction set of the original Turing machine is a program. Maybe we write in C, a C program. And the inputs, like for an addition, you give some inputs. And this program and inputs, to both this combined, we give to our laptop. and our laptop does something in the CPU level and gives back the output as a sum of both numbers. Similarly, this universal Turing machine is like our laptop. It takes the instruction set of the program of some Turing machine, like can multiply or add or any other program, and it takes some inputs which it took for the computation, and just gives the output what the original Turing machine would have given. Like, for example, if there's a Turing machine add which adds two numbers. So if you give the universal Turing machine the code of the add and the two numbers which you want to add, it will give the output as a sum of those both numbers, like how the add machine would do. Now we go to Church's thesis. So like Church's thesis states that any algorithmic problem that can be solved by an algorithm can also be solved by a universal Turing machine. Now this is a very important thesis because this shows that Turing machine, this states that Turing machine is the strongest computable device we have. Nothing can be stronger than that. So anything we can compute should be computed by a Turing machine. So it asserts that Turing machine capture the essence of what is computable, and they provide a comprehensive model of computation. So like nothing outside, if something can't be computed by a Turing machine, then it cannot be computed by anything else. That's what they try to say. But although this is accepted within the field of theoretical computer science, it is still a hypothesis and it has not been proven. So it could be an active research to disprove it. So now we go to the main topic of this lecture, of this talk, which is going to be the halting problem. So first of all, we wanted to decide, like, if we have a program and its initial input, we want to come up with an algorithm which can decide if this program will halt or not. So maybe if we have a while loop, which has a terminating condition that uh, your uh, your variable should be less than some natural number. But the problem is, like, in your code, you forgot to write the increment step. You didn't write I plus equal to 1 or something. So can you give it to a computer code and so that the code will say that, hey, this is going to run forever. So we want to find an algorithm if something can do that. So that's what the halting problem asks. So it asks if there's a single algorithm which can determine the halting of every program given its initial input. So maybe like if you're given I less than 5 and you keep on doing I plus plus in the program. Definitely if you give like an input I equal to 3, it's going to halt. But if you give an input like I equal to 7, it's not going to halt. So like the halting of a program even depends on the input you give. So the input is also necessary. So Alan Turing proved that no such algorithm can exist in his Turing computer for the halting problem. So Turing tried to solve the halting problem with a Turing machine. So he assumed that there's a Turing machine called halts, which tells if a Turing machine halts or not. Very simple, right? So like input of halts is the instruction set of a Turing machine and the input of the Turing machine. So like maybe input of halts is a specific program, maybe to multiply two numbers. And the input may be like two numbers like 10 and 50. And then halts is going to give output like yes or no. Halts will give yes if it halts. Halts will give no if it doesn't halt. So if a Turing machine adds two numbers, the input of halts will be the instruction set of the Turing machine and the two numbers to add. So halts will tell the program if the add program will halt or loop forever. So let's see some implications of assuming this. This means that we can make another Turing machine called not halt. So we are going to take a program as an input and we are going to make it like this. So not halt is a program which makes two copies of that program, gives both the copies to halt and asks halt if that will halt. If halt say it will halt, then not halt will loop forever. If halt say it will not halt and loop forever, then not halt will halt. So it's like trying to give a paradoxical situation where If halt say it will halt, then I'll not halt. If you say I won't halt, then I will halt. It's trying to defy what halt is saying. So now what happens when we run not halt given the program not halt? So this is what happens is when you give the same program instruction not halt to not halt. So first not halt makes another copy of not halt and it gives it to halts. So by making that copy, it makes if halts on the program not halt, given the input not halt, if it halts, then not halt will loop forever. If it loops forever, not halt will halt. I think you guys can see the problem, like if this halt, this loops forever, and if this loops forever, this will halt. So now we try to make a contradiction with this. So if halts of not with the program not halt and the input also not halt, it halts. Then according to not halt with the input not halt, it will loop forever. But halts of not halt comma not halt gave that halt. That means not halt when given the input not halt should halt. But as it is looping forever, it's a contradiction. Now, similarly, if halts of not halt comma not halt loops forever, then according to the instruction of not halt, it's going to halt. But this is also a contradiction because according to halt, it should have looped forever, but it's halting. So on basis of this, as the only assumption made was there exists a Turing machine which says if a program halts or not. So this contradiction implies that such a Turing machine cannot exist. So what does this mean for us? So this means that the universal Turing machine can run all the computable problems or all the things which other Turing machines can do, but it cannot decide if a program will halt or not. This means that our computers cannot decide if our program is actually halting or will it run later. So we might think that the computer is just stuck loading here forever. Why can't it just tell me that it's stuck in an infinite loop and just try to read through it? But no, they really don't know if you're stuck in an infinite loop or will the program start making progress again? So this shows that the halting problem is undecidable. We cannot say yes or no to the halting problem. So this also proves that mathematics is also not decidable. So why do we care now? We have shown that mathematics is undecidable. Let's go. Who cares right now? We are done with it, right? So why should we care of something which has no future things of learning it? We can just maybe learn it as a statement that mathematics is undecidable and be happy with it. But no. The thing here is, why do we still care about Turing machines is because we haven't proven the Church-Turing thesis, first of all. It's still a thesis. Though it is probably true, we have not proved it formally. And one more thing is there's another thesis which states that any computation which can be done by any other type of computational model can be done with the Turing machine with at most a polynomial slowdown. This means that if you have some arbitrary computational device which does a computation in polynomial time, then there exists a Turing machine which can also do it in polynomial time. So this, and if Turing machine does it in exponential time, this means that anything else will do it in exponential time. So this gives rise to complexity theory, and the basic definitions of P and NP depend on if the problem can be solved in polynomial time in a Turing machine or not. So Turing machines are still very relevant and very important for theoretical computer scientists who read on complexity theory. So the conclusion is, at last, all the three problems given by Hilbert were proven to be false. Turing gave theoretical computer science and computational complexity theory, which are very important theories and what we are learning now. He has already also given birth to other aspects of computer science like automata theory and more, and cryptography also. So basically, he has given birth to like majority of computer science. His impact on the world of computing cannot and beyond cannot be overstated, and we should always celebrate him as the founder of computer science. Thank you for giving me the opportunity. It was presented by R.K. Shishir, and I would also like to thank Aditya Gupta for editing the presentation and helping me a lot with the presentation work. He made the presentation very clean so that it would be more understandable. Thank you.